Hi, so this video is going to be your review for the Unit 4 exam. I'm just going to go through a few things, and one really important thing I'm going to show you is how to use StatCrunch even if the MyMathLab or MyStatLab tool doesn't work. Okay, so what we're going to start with first of all is just looking at some. This is for Chapter 10, so we're going to start with looking at some scatter plots and then looking at what the R values are that go with them. So here I have three scatter plots pulled up, and if you look at the three of these, if you compare them, this one on the left has the most clear linear trend. The points are the closest together and the closest to being in a straight line pattern. If you notice, this one also has the R value that's the closest to 1 out of any of the three. Now this is a positive R value because you can see the points are going up generally as they go from left to right. If they were going down from left to right, then it would be a negative R value. The scatter plot in the middle, that one, really you can't see any kind of trend. There doesn't seem to be any pattern whatsoever. Notice for this one, the R value is negative, but you really wouldn't be able to tell if this were negative or positive. The most important point here is that the R value is really close to 0, which means there's no linear relationship at all. And last of all, this one on the right, this one looks like it has a positive trend, so the points seem to be going up from left to right. Not in a very obvious straight line pattern, but they do seem to be trending up from left to right. So notice this one has an R value of 0.719. So it's not nearly as close to 1 as the one on the left of the screen is. That one was 0.908, and there was a much clearer linear pattern. This one is 0.719. And there's a pattern, but it's not super clear. Okay, so that was the first thing I wanted to talk about. And next I want to talk about what happens if you're taking the test and it won't give you the option of opening a data set in StatCrunch. I tried to get all of the problems set up so that it would, but sometimes MyMathLab doesn't do exactly what I want it to. So I just want to make sure that you have another option if that doesn't work for some reason. So I'm just going to show you an example. This is just a problem that was in your homework. So if you're looking at a problem like this, what you should be able to do is if they give you a data set like this in a table, you should be able to click on the little boxes at the upper right side of the table, and it should give you an option to open in StatCrunch. So if we went ahead and clicked on that, then it's going to put your numbers, even the column headings, in StatCrunch for you. Now if it doesn't give you that option, so if it comes up here and it only says copy to clipboard or open in Excel, there's still another way that you can use StatCrunch for this. It just means that you'll have to type in the numbers yourself. So if it doesn't give you that option, then what you need to do is just open another browser window. And what you need to do is just go directly to the StatCrunch website. And to do this, you can just type in statcrunch.com. And it'll take you there, and it should, if you're already signed into MyMathLab, it should not make you sign in. If it does make you sign in, just use the same login ID and password that you used for MyMathLab. So once you get this pulled up, then what you would do is, if you want to put in some data, just click on Open StatCrunch. And then you're just going to enter the data that they gave you. So in this problem, we had the systolic blood pressure and the diastolic. So I'm going to go ahead and type those in for my column headers just so I know which one's which. And then I'm just going to type the numbers in there. Oops. And then once I get done typing all the numbers in, I can go ahead and do whatever I need to do for the problem. So that's always another option that you can use. Okay, so now what we're going to do is look at a few problems, and these are from some different homework assignments I've given in the past. So these will be either to do with Chapter 10 with linear regression, or to do with Chapter 11 where we had tests for independence and tests for goodness of fit. Okay, so we're going to start with the linear regression. So here's a linear regression problem. And what we're looking at here is the mortgage rate, the mortgage interest rate, versus the number of months homes were listed for sale. And we want to see if there's a relationship between those two. So I already went to StatCrunch and typed in the data that's in this table. And for this one, since we're only talking about the interest rate in the months, I didn't type in the years. I didn't need to do that. So in this first part, where it asks you to find the linear correlation coefficient, then what we're going to do in StatCrunch is do the linear regression procedure, and that will give us the correlation coefficient. So I'm going down to regression, simple linear, and then for my X, I'm going to put in interest rate, and for my Y, I'm going to put in months. And if you're in my math lab and it's letting you open things in StatCrunch, it'll already have the column headings there for you. Okay, and then all I have to do is go down to the bottom and click on Compute, and that automatically gives me a whole bunch of information. It's going to give me the linear regression equation right here. It also gives me the correlation coefficient, the R-value, right here. And then down here in this line, or in this row that says slope, it's going to give me the test statistic and the p-value. Just remember that you're looking for the row that says slope. Okay, so from this, I could answer this question. So I've got the linear correlation coefficient, so my R is negative 0.569 if I'm rounding it to 3 decimal places. Okay, and then my linear regression equation in StatCrunch, the variable on the left is always the Y, and the variable on the right is the X. And they use the column headers instead of Y and X. So this would be Y equals 16.450 minus 1.656 times X. So there's my equation of my linear regression line. Okay. Then the other thing that this will do automatically for you is it will give you a scatter plot. So if I go back to StatCrunch and I click this arrow on the bottom right, it will take me to the scatter plot. Now this one, because there weren't very many data points, it's kind of hard to tell what's going on here. But here where it's asking me how well the linear regression line fits the data points, not especially well. There are a couple that are way off the line, like this one. So that one we could probably consider an outlier. But this is a way to get the scatter plot, if that's what you're looking for. Now the other thing that we can do, going on to this third part C down here, is if we're trying to do a hypothesis test, so if we're trying to confirm that there really is a linear relationship between the variables, then what we would look at is the test statistic and the p-value. So then we're going back to this row of our table over here that has slope. So our test statistic is under where it says t-stat. So our test statistic is negative 1.955 if we round it to 3 decimal places. Our p-value is 0.0864. Okay, now for the conclusion of this, and this is where it's a little bit easy to get mixed up, I know. This told us to use a 5% significance level, so significance level of 0.05. So what we're testing is whether the p-value is smaller than the significance level, so if it's smaller than alpha. If it is, then we have a positive conclusion. If it isn't, we have a negative conclusion. So for this one, if we compare our p-value, which is 0.0864, and our significance level, the p-value is actually bigger. So the answer to this is no, or it's false. So what that would mean is that for our conclusions, they're negative. So we would not reject the null hypothesis. And we would say there's not sufficient evidence to support the claim. So there's not sufficient evidence that they're of a linear correlation, because that was our claim up here. Okay, so now in part D, what it's asking is to estimate the number of months a home would have been listed for sale if the interest rate were 5.5%. So the answer to this and how you get there depends on what you came up with for your test result up here. What we came up with up here was that there's not sufficient evidence that there is a linear correlation. So that means we can't use our regression equation to make this estimate. So the only way that we can estimate this number of months is by using the average of the numbers of months up here in the table. So to do that, what we would need to do is go back to our StatCrunch and just find the average of the numbers of months here. So to get that really quick, we can do stat and summary stats in columns. And we just want the average for the months. If we just leave everything like it is here and just do compute, it's going to give us a whole bunch of other information. But it gives us what we want, which is 6.55 for the mean. So the only estimate we can make for the mean is just listing the average of the number of months. So that would be our estimate. Okay, then if we go on, we've got another question here, and that is to take the data that we already had and delete the values for the year 2002, and then go ahead and repeat all these questions. So our values from the year 2002 were the very first row of the table. So I'm just going to go back and just delete these. And then I'm going to redo my linear regression. I'm just going to go ahead down here and click compute. And then it gives me everything I want just by doing that one procedure. So what we have here, here's our regression equation. Our correlation coefficient this time is quite a bit higher. Before it was negative 0.569, and this one it's negative 0.807. So it's closer to -1, which means it's a better relationship. We can look at our test statistic down here is negative 3.62, and our p-value is 0.0085. So our p-value is much smaller than it was in the first question. If we look at our scatter plot, and again, with so few data points, it's kind of hard to tell how well this fits the data, but we do have most of the points a little bit closer to the regression line. Okay, so if we were just looking at the part C and D for this one, for part C, we could list our test statistic, which would be negative 3.62, our p-value, which would be 0.0085. So what that would mean is that our test conclusions are going to be positive. Again, we're comparing our p-value of 0.0085 to our significance level, which was 0.05. This time the p-value is smaller than the alpha. So we have a true statement, which means our conclusions are positive. That means that we do reject the null hypothesis, and we'd say there is sufficient evidence of a linear correlation. Okay, so those are kind of the two things that you can run into. And just remember, in something like this where we had a negative R-value, that means that our basic trend is that our data is going down from left to right. You can see with the regression line here, it's going down from left to right instead of going up. Okay, so the next thing we're going to look at is the stuff from chapter 11. So we're going to start with the goodness of fit tests. Okay, so this first one is about weights that are reported or actually measured. So what we're trying to find out is if the last digit happens with the same frequency or not. If it does, then the weights were probably measured. If it doesn't, then they were probably reported, because most people, if they tell you their weight, they're going to round it to the nearest 0 or 5. Okay, so what we're looking for in this one is whether the last digits occur with the same frequency. Another way they might talk about this is whether they're uniformly distributed. So same frequency is the same as saying uniformly distributed. Okay, so what we want to do here is a goodness of fit test. And I already went through and put the data into StatCrunch. Now for StatCrunch, when you're doing this procedure, you have to put in the expected values. So I left another column in this table to put the expected values in. And how you get these is that you take the total. So it tells us here that we have 80 randomly selected students. So we've got a total frequency of 80. And we're going to multiply that times the proportion that we expect each one of these to be. So whatever our distribution is claimed to be, then we're going to multiply those decimal values times our total. So in this one, since we're saying it's equally distributed, and we have 10 different categories, so we have 10 different categories, that means that each one we would expect to have a proportion of 1/10. So we're just going to take 1/10 times 80 to get our expected value for each one of these. So that's just going to give us 8. And for this one, it's going to be the same for each one, since that's what we're looking for, is that the distribution is equal with all the categories. Okay, so that's what we would put into StatCrunch for our expected values. Now, the other thing with StatCrunch is that if you are looking for an equal distribution like this, you don't actually have to put those numbers in another column, because it will ask you if you're expecting an equal distribution. So we could go ahead and do our goodness of fit test in this case without putting those numbers in. So if we go to Stat and goodness of fit and chi-square test, then it wants to know where our observed values are. So that would be the frequency column. And then here's where we can tell it we expect all cells to be in equal proportion. So there's the shortcut for that one. And then we would just do compute, and it will actually give you what those expected values are. So on your test, if it's asking you something like this and it wants you to fill in the expected values, if they're all equal distribution, you can go ahead and let StatCrunch do the work for you. It won't work if the distribution is different for each category, but if it's a uniform distribution, or if they're all supposed to be the same proportion, then you can get those expected values just by doing this. Okay, so this gives us all the information we need. It gives us our expected values. It gives us our sample size, which is 80. So our sample size is 80. If we're looking at a hypothesis test, our degrees of freedom is 9. StatCrunch also tells you that right here under DF. The test statistic is under where it says chi-square, so that would be 23.5. And our p-value is 0.0052. Okay, so since we were supposed to use a 0.05 level of significance, again, the question that we're asking is the p-value smaller than 0.05, which was our significance level? So the answer this time is yes. That means we have positive conclusions. Now, for a goodness of fit test, the null hypothesis is that the sample values do fit the distribution. In this case, the claimed distribution was that they were all equal. So if we have positive conclusions, that means that we're going to reject the null hypothesis. which means that basically that the values, we're saying the values don't fit the claimed distribution. In this case, that would mean that no, they're not equally distributed. So the last digits of the weights are not equally distributed, which probably means that they were reported instead of actually measured. Okay, let's do another goodness of fit test, and this is going to look a lot like what you're doing in your discussion. Because this one has to do with M&Ms. Okay, so this one, we've got the same idea. We've got a sample, and this was a big sample of 2020 M&Ms. We've got our proportions that the Mars company claimed that they should fit. And to do this in StatCrunch, we're going to have to fill in the expected column. Since this isn't an equal distribution that was claimed, we're going to have to fill in those numbers. Okay, so for this one, we're going to take our total sample size, which is 2020, and multiply it times each one of our different proportions that was claimed. So for the blue, the claimed percentage was 24%, so we're going to take our 2020 times 0.24. We're just converting that to a decimal. So this is going to be 484.8. So I'm going to calculate all these, and then I'm going to put them into StatCrunch. So then for the orange, the claimed proportion was 20%, so I'm going to multiply my sample size times 0.2. That gives me 404. For the green, it was 16%. So that's going to give me 323.2. And when you're doing these, don't round the numbers unless it's something that's repeating a lot, but in that case, take it out to several decimal places. Okay, and then for the yellow, we're going to have 2020 times 0.14. So that would be 282.8. For the red, it's times 0.13. And for the brown, it's the same one because it's times 0.13. Okay, so I'm going to take all of those numbers and enter them over here. Okay, and then I'm still trying to do a goodness of fit test, so I'm going to use stat goodness of fit chi-square test. So my observed values are the frequency that I got from this table. That was from my actual sample. My expected values I put in the column that I named expected. So this time, since it wasn't all in equal proportion, I actually have to tell it what those numbers are. And I'm going to do compute. And this shows me my entire table that I already put in there. And it gives me all that other information also. So I have my sample size is 2020. My degrees of freedom is 5. My test statistic is 10.87. I rounded to 2 decimal places. my p-value is 0.0541. Okay, and for this test, the null hypothesis is that the colors do fit the claimed distribution. So the candies do fit the claimed distribution. So that they do fit these percentages up here. The alternative hypothesis would be that they don't fit that distribution. For our test results, we're asking, is the p-value smaller than our significance level? Our significance level was 0.05. And the answer to that question is no, because our p-value is a little bit bigger than 0.05. So that means we have negative conclusions. So that means that we do not reject the null hypothesis, which in a roundabout way means that we're accepting the null hypothesis. So we're saying that the candies actually do fit the claimed distribution. So we can say there's sufficient evidence there's not sufficient evidence. This means in a roundabout way we're saying that they do fit the claimed distribution. Okay, so those are the two ways that you can have a goodness of fit test, either with a uniform distribution or where it says they're equally distributed, something like that, or where they give you the distribution, different percentage or proportion for each category. And in that case, you have to figure out the expected values for yourself. Okay, the last thing we're going to look at is the test for independence. So in this problem, this was a study that looked at the common cold and whether echinacea was effective in dealing with cold infections or not. So we had 3 treatment groups. One got a placebo, one got a 20% echinacea treatment, the other one got a 60% echinacea treatment. And what we're testing here is whether the status of getting an infection or not is independent of the treatment group. In other words, whether the echinacea treatment is effective or not. Because if it's effective, then our status for infection or non-infection is going to be different for the echinacea treatment than it is for the placebo. Okay, so for this one, we've got our information in StatCrunch. So we're just doing a test for independence. In this one, there isn't something in here that actually says test for independence. What you have to do is go to tables and contingency, since this is a contingency table. And what we have here is a summary. We don't have raw data. If we have it summarized in a table, then it's with summary. Okay, so for this, you need to select all the columns that have the numbers in them. So you have to select all 3 of these. And then For your row labels, that was in the status column. And then we're doing a chi-square test for independence. Okay, so it should give us back our table. It also gives us a total row and a total column. And then it tells us our degrees of freedom. And this, where it says value, that's our test statistic, and our p-value is under p-value. So we have all the information we need. Our degrees of freedom is 2. Our test statistic is 2.93. Our p-value is 0.2316. Now again, in this one, if we're looking at a hypothesis test, we're comparing our p-value to our significance level, which was 0.05. So we're asking, is the p-value smaller than 0.05? The answer to that is no, so we're going to have negative conclusions. That means we do not reject the null hypothesis, and there is not sufficient evidence to support the claim. Now, with the test of independence, the null hypothesis is always that the two variables are independent. And the alternative hypothesis is that the two variables are dependent. So in this one, if we're having negative conclusions, that means there's not sufficient evidence to support the claim that the infection status and the treatment group are dependent. So in other words, there's not enough evidence to say that they're related. We can say that they're related, associated, or dependent, whatever. In terms of this problem, that would mean it's saying that the echinacea treatment isn't making a significant difference to the infection status. Okay. One other thing that I forgot to tell you at the beginning is that there might be some problems on the test where they give you just an R value. So this is going back to the linear regression. So if you have the R value, you can find the test statistic. And that was just a formula that was in your Chapter 10 notes. So if you're just given the R value and it wants to know whether there's evidence of a linear relationship, then you'd want to find the test statistic. From the test statistic, you can find the p-value and make that determination. So once you have the test statistic with that formula, then you would find the p-value. And to do this, this also is in the Chapter 10 notes. You use TCDF on your calculator. So you'd use TCDF, put in your test statistic, and then put in a large positive number, and then put in the degrees of freedom, which is your sample size minus 2. Now, to get your actual p-value, you have to multiply this by 2.